Hi all, I'm Rajiv Prabhata, and I'm a senior software engineer at AWS. I'll be starting us off with a tour of what I believe to be the backbone of any multiplayer solution, the transport layer. The transport layer is ultimately responsible for a lot. To meet these needs in O3DE, AZ networking was developed with these criteria in mind. Starting from the top, having a streamlined API that's readable, concise, and understandable is key. A significant amount of boilerplate was reduced by relying on code generation. In total, AZ networking is about 13,000 lines of code, including the generated artifacts. To give a better sense of how the code gen looks, here's how AZ networking's core packet types are generated. As you can see, our XML definition is fairly slim. It defines packets for connection initiation, handshake, disconnection, heartbeat, and fragmented packets. Let's take a brief look at the generated output with a focus on fragmented packet, given it's our densest type. Here we have the header definition for fragmented packet. As you can see, it defines the members and a variety of getters and setters related to them. It also defines some common implementation based on some interfaces. Moving over to the INL, we see the implementation for many of the aforementioned getters and setters. And last but not least, we have the CPP, which defines some basic business logic related to the members. This includes, importantly, serialization. Moving on, let's talk about reliability. AZ networking provides standard options for sending data reliably over a socket. First is a TCP implementation, which is reliable by default. TCP is very feature-rich, but doesn't offer control over its congestion avoidance and reliability. Fortunately, a UDP implementation is also provided. Packets on UDP can be sent reliably or unreliably, with a variety of configuration options, so you have the level of control you need. To ensure that transport holds up over a variety of network conditions, there are configurable options to simulate artificial latency and artificial packet loss. Given UDP and TCP, you may wonder how data can be protected. After all, in any multiplayer simulation, there are always malicious actors. To ensure there's a baseline of security, AZ networking provides the following. DTLS and TLS integration by OpenSSL for UDP and TCP connections respectively is available. It uses a simple model in which you only need to direct your endpoints at certificates and the rest handles itself. DTLS and TLS are an optional part of the transport handshake, which is used to validate a connecting endpoint. Once transport has completed its handshake, the bulk of gameplay traffic is expected to be handled by implementers of iConnection Listener. This implementation relies on generated packets, which helps mitigate attacks involving spoofed datagrams and is time windowed to mitigate time delay based exploits. As an example of iConnection Listener, let's take a look at the multiplayer gem. Here's a look at multiplayer packets XML. It defines some connect and accept packets to perform some additional handshake logic, plus packets to handle entity updates and remote procedure calls. In the multiplayer system component header, we can see handle request functions for each packet type. There, the contents of the received packet can be handled as desired by the user. Developers can also perform gameplay-based handshake logic by marking packets as part of a handshake. This ensures only handshake packets will process until a developer-defined function indicates the handshake is complete. This is where the isHandshakeComplete function comes into play. In multiplayer system component CPP, this checks a bool which is modified on receipt of the connect or accept packet, depending on the endpoint in question. You can see the connect packet doing just that right here after clearing some logic. Jumping back to the XML, you'll notice connect and accept both have this handshake packet true value. This indicates that only those packets will process, while isHandshakeComplete returns false. All other packets will not process. Consequently, reliable packets will be resent until they can process, while unreliable packets will be the user's responsibility to resend. We've talked about reliability and security at this point, but what about speed? Naturally, the less lag a player experiences, the better their user experience. You might recall UDP was implemented specifically for the sake of performance, and that's just the start. Packet fragmentation for UDP is available so large packets can be sent on your terms. Any compressor can also be plugged in via the iCompressor interface. The O3DE Git repository has a zlib implementation of the iCompressor interface as an example in the multiplayer compressor gem. Serialization of data types is also available, including delta serializers, so you can control the footprint of data being transported. Serializers can be specified per type, which are then invoked via generated code, as we saw earlier with fragmented packets. Last but certainly not least, network traffic metrics are available so you can measure the network performance of your simulation and tune it appropriately. AZ networking has also been profiled to ensure that its logic isn't holding data up. In fact, profiling shows a 1-byte reliable packet sent on UDP roughly takes 35 microseconds. With all features enabled, such as DTLS and compression, this increases to about 55 microseconds. To ensure confidence, the solution was put through a variety of test runs to battle test it. You can find a publicly available soak test for AZ networking on GitHub. The soak test sets up and saturates AZ networking connections with traffic and is highly configurable so you can test a variety of feature combinations. This makes it well suited to automation. The soak test was leveraged extensively throughout the development of AZ networking to ensure that every feature included functions at a high level, with no observable degradation in resource utilization, network performance, and data integrity. This includes a variety of combinations of features. Runs have so far exceeded 72 hours. If you're interested in learning more, you can check out O3DE's public documentation. You can also find this code publicly available on GitHub. I hope you've enjoyed this brief overview of AZ networking. Thank you for your time.